Welcome to the Numerical Derivatives Code Along. If you haven't already watched our Numerical Derivatives with Honey Badger video, you'll want to check that out first. And let's give it a shot now that we're actually writing the code. Here we are in Python, we're in Spider. I have my console here on the right, and I have my actual script on the left. I've saved this blank file as numerical derivatives example.py. Let's begin by importing pylab from pylab. Import star. We will begin by making an array to hold our time steps. What will it start at? It'll start at t0. We'll let that be 0, 0.0. T final will be, let's say, 2 times pi divided by 3, 2/3 of pi. We'll say 2.0 divided by 3.0, just to make sure we know these are not integers. They are floating point values that happen to be integers 2.0, 3.0, and in steps of dt will equal t final minus t initial divided by the number of time steps. So we need to know what the number of time steps will be. Let's let that be 12. I have my dt. Now I need a t array. T will be a range from t0 to t final in steps of dt. And we're going to define a function. I'll let my function be, let's keep these together. Let's have the function be sine of t. And we will plot those. Plot t, comma f. I'd like to see those data points nice and clearly, so I will let them be red, connected circles. That's r dash lowercase 0. The r gives me red, the dash gives me connected points, and the 0 gives me little circles. Let's take a look at those. We will run the code, and we should get a plot. Take a look. There it is. We have the function sine, but only every 12th. Did I say 12? Yep, only every 12th of the distance between 0 and 2 pi. So we can see we get past pi over 2 here, where there's a maximum in this function, and just down a little bit. Now we would like to take derivatives of this data as well. So let's remember the first function we're going to use, we'll take our right derivative. What does that mean? Well, let's look more closely. If I look at these data, I know that this is f0, over here is f sub 1. Of course, t0 is this one right here, t0. And what if I want to know the slope here at value 3? Well, the derivative at value 3 will be f4 minus f3 over t4 minus t3. What does this mean? At value 3 here, I'm taking this slope, this rise over run, and storing that slope in this value. So each value gets the slope to the right of the value itself stored in it. That's what we mean when we say we're taking a right derivative. In the actual code, we'll use square braces to tell us which value of the array we're looking at, like this. So let's put this into our code and see how it looks. So we're defining our right-handed derivative. We define a function in Python with def. That's defining the function. We'll call this dir right because it's the right derivative. And it's going to take as inputs two functions, f and t. That's the function and the thing we're taking the derivative with respect to. So we're taking df dt. I'm going to define an empty array, zeros. And that will be size of t. F and t better be the same size or this won't work. And now I'm going to have a for loop for I in range. This is the right derivative, so 0 is fine. We can go up to size of t minus 1 because the last data point doesn't have a right neighbor. When I go all the way to the right end of an array, I won't have any more right neighbor. Colon begins my for loop. Now I'm going to say d of I will equal f of I plus 1 minus f of I divided by same quantity but with t's, too many parentheses. These are going to be t's. So I have the change in f to the right, I plus 1 minus I, change in t in the denominator, t I plus 1 minus t of I, and our function needs to return d. That's going to be our right-handed derivative. Let's make sure that it works first. So I will say if this function represents position, then the first derivative would be velocity. So I'll say VR, which will be v using the right derivative. That's what VR is meaning in my head. So I'm going to say that's going to be dir right of f comma t. And let's plot that plot t comma br. Let's make it black triangles, and they are also connected. So this is black, the hyphen means connected, and the V means that these are downward pointing triangles like the shape of a V. We're going to put these in figure 1, and so that I can run this code multiple times and clear the results each time, I'll say CLF, that's clear figure, and let's give it a run. I take a look at the data, and there it is. I have, let's get me out of the way. Here's the function itself, sine in red, and our numerical estimate of the derivative, which should be cosine, which is looking pretty good right up till the last point, because we didn't have any value to put in here on the right endpoint. That is where the right derivative fails. So let's see what we can do if we take the left slope. Let's run this again and say what I mean. What we've been doing is, say for this point right here, I'm taking this slope, rise over run, and storing it in here. That's our right derivative. Now we want to do the opposite. I want to take this left slope, so I'll take, suppose this is f0, 1, 2, 3, 4, 5, f5. Instead of taking 0.6 minus 5, I'm going to take 5 minus 4 and store this slope in there. And that's what I mean when I say a left derivative. Let's give it a try. Get that plot out of the way. Anytime I'm writing a function that's basically the same with a few changes, I'm going to use copy and paste because my time is too valuable for typing, right? I'm going to change this right to left. It's also less error prone if you just copy and paste. So I'm going to take size, instead of from 0 all the way from the left endpoint to 1 short of the right, I'm going to go from the not 0th but the first point all the way to the right. So that's going to be, instead of 0 to size minus 1, it'll be 1 all the way up to size. And here we're going to take I minus 1 and I minus 1. That's what it means to be taking the slope on the left of point I. We'll do that too, and I'll say v left. That's the velocity estimated using the left-handed derivative. That will be dir left of f and t. We'll plot that too. Let's use blue. Same idea, but v left, and b for blue here. We can use squares just to make it extra clear in case this is plotted without color. So we can see here I have two estimates of the derivative. They have the same general shape, but this black estimate fails on the right. That's dir right. And my blue estimate fails very clearly, look at this big jump, on the left end. We can fix that by using the formula for the left derivative for the first point of the right formula, and the formula for the right derivative in the last value of the left derivative. Can you keep those adjectives straight? Let's give it a try. I'm going to take, in my right function, d of the last point, and we can count backwards, so -1 means the last point. That's going to be some ratio of f and t. I know it's going to be f of -1 minus f of -2, and the same exact thing for t. And we have a similar substitution of the opposite formula in the left point. So d of 0, oh, this is a pretty simple error. This needs to be not inside my loop. There's no reason for that to be a loop because there are no i's here. So we get out of a loop by tabbing out. Remember, anything that's tabbed inside this for is inside the for loop. Once we get out of that level of indentation, here's 1 indent, here's 2 indents. Once we're out of that level of indent, that is going to be outside the loop. So for my 0th value, I'm going to take f of 1 minus f of 0 divided by t of 1 minus t of 0. So those are the two left points that give me the estimate of slope there. Let's rerun this, and I have fixed this value, so I just get the same value for both derivatives on the right endpoint and the same value for both derivatives on the left endpoint. 0, 1, 0. Oh, here's my problem. I had a division by 0 there. T of 1 minus t of 0. Let's give that another try. And now you can see I have this working properly here. So both those derivatives are not right. The blue derivative is too high and the black derivative is too low, but the real derivative is in between these two here. I happen to know that the derivative of the function I've chosen here, sine, the actual derivative is cosine. So I can say d actual equals cosine of t, and plot that here. Plot t and, what did I call it? D actual. That's the actual derivative. Always better to copy paste than to type and make a spelling error. We'll let this be, let's say, yellow, and we'll make it thicker. Line width will equal 3. Let's give that a look. So this bold yellow line here is the actual derivative, and you can see that these two values are straddling the real value of the derivative here, which is right there. Do these approach each other when I make my time steps smaller? Let's give it a try. Instead of 12 time steps, let's have 24 time steps. And you can see that these values are pinching closer to that actual value of the derivative, yellow. They've gotten closer to each other. And this is all looking smoother. Everything gets smoother when you have more data points. If we're collecting data with our actual ultrasonic ranger, like we did in class, I just need to have more data points per second to calculate the distance to that mass as it moves up and down on the spring. So we can take the average of these two derivatives to give us the central derivative. It's going to look pretty similar. And it's the value that we'd actually use rather than dir left or dir right in practice. So let's copy our boundary fix here, the value for the right end, the value for the left end. We want both of those in this third function. Moving too fast here. I have dir right, dir left, and now we're making dir center. And that's going to make the same. We need to compromise on both ends of the interval. So I'm going from the first value, which is actually the second value, because remember we start counting from 0, up to the next to last value. We're going to have f of I plus 1 minus f of I minus 1, and t of I plus 1 minus t of I minus 1, except for on the two endpoints where we have to compromise and use these single-sided estimates of the slope. Let's give that a try. We'll plot v center oh, what is this? I need to have v center will be dir center. So in these three lines, we're actually taking those derivatives using our functions, and we're storing the output of the function in arrays for each estimate of derivative. Let's make this magenta, and we'll use squares. Maybe we'll go back to circles. And so our magenta should be very close to our yellow, much closer than the other numerical derivatives. And I see that those magenta circles there, they're lying right on top of the yellow. Let's zoom in a little bit and go full screen. And zooming in, just a few data points here. Look at how close those are. The magenta circles are right behind the actual value. Of course, they are not exact. Look, there's a little separation there. Not perfect, but they're much better. You can go back one level of zoom here. Much better than the black or the blue. So that's why we like to use centered derivatives whenever we can. We don't really even need these dir left and dir right functions. They're actually not very good. But they give us the concept of how to take these derivatives. So looking at that graph again, note that we're taking, when we take this derivative, when I take the right derivative, I'm taking this slope and storing it in this point. When I take the left derivative, I'm taking this derivative, this slope, and storing it in this point. And when I take the center derivative, I'm taking the slope from the right to the left and storing that slope in this middle point. Here, on the next point, I'm taking this slope and storing it in this point. Taking this slope, storing it in this point. So each slope I'm storing in the point that's at the midpoint of it. Sometimes this is called a midpoint rule, midpoint derivative, or centered derivative. So that's a review of our numerical derivatives. We'll take a look at how well behaved they are in the next video.